Okay, good afternoon, everyone. I said I would make a video of the Chapter 6 review on pages 213 and 214 of your book. So please follow along and you can obviously stop the video at the points where you need to listen again or view the process again and see how the answer is worked out. So please follow along and let's get started. So I'm going to do questions, all the questions except for number one here. I will post like the little marking key for these as just examples of those situations later at the end. So I'm not going to do number one or number four. And I'm also not going to do the last two questions. I think they're questions number 20, 19 as well, as they talk about a pulley and a sketch of a graph about force, weight force, whatever. Okay, so let's get started with question number two. And I'll just, this left side, I'm just gonna have the questions and I'll underline the important information in here, and then I'll do the working here on the right hand side. So we got a push trolley on a horizontal path, and he's doing it with a force of 30 newtons, which is to maintain his speed. So that means that the net force here will be zero if we're keeping the velocity constant. Okay, so what else is here? His mass is going to be 35, and it wants us to find the total horizontal force. Okay, that he would need to have or provide so that there is an acceleration of 0.5 meters per second squared. All right, so let's see what we need to do here. So for him to achieve this acceleration, he needs to apply a force more than the 30 newtons here, because the 30 newtons is just enough to overcome whatever friction force there is. So let's work out what is the net force first that causes acceleration. So we'll do this one. We got net force equals mass times acceleration. And we have that information already. He's 35 kilograms and he's accelerating at 0.5 meters per second squared. So that would require 17.5 newtons of net force to accelerate the trolley that much. Okay, so they want us to find the total force though, and so that total force to give us that net force would be the 17.5 from our net force plus that 30 that he was already pushing with just to maintain a constant velocity. And so that total force then for us would be 47.5 newtons. Okay, and you see I have 1, 2, 3 significant figures. Doesn't matter how many decimals or whatever, it just matters how many numbers, real numbers there are to round my final answer. Okay? All right, so that answers that question. We'll move on down and we'll look at number 3. And same here, we'll just look at number 3 here as well. Okay, so what we have here is a single force. Again, a single force of 25 newtons. And it's applied to a 15 kilogram ball. And that's applied for a time. So we have an applied force. Okay, you guys should take the practice of writing things down, or as you underline, it's even helpful to write it out again. And for a time of 4 seconds. Okay, so it's asked us what is, if the ball was initially at rest, so initially at rest, that means u is 0. What is the final speed? Okay, so v is what? Well, I know I have u, v, and t here, and I know they're is a force applied to a mass. So I know there must be some kind of acceleration happening to the ball. So let's find what that is first, because that acceleration is needed to help us find the final speed. So acceleration, again, there's my base equation, net force divided by mass equals acceleration. So we have, it's only one force, so that is the net force, 25 newtons divided by 15, and what we end up getting is 1.67 meters per second squared. Okay. Um, and then it says we need to find the final velocity, and then based on this information now, I know, looking at my formula data sheet, that this equation has all four of those variables. Okay, this is 0 plus this amount, 1.67, times the time of 4 seconds. Whoops, I'm running out of space here. I'll just add a little bit to the right. And it won't. Okay, I'll just make my screen a little bigger there. Force, there it is, 4, and then when you multiply that out, you should get 6.67 meters per second. Okay, and that's question number 2. So we'll put this back, and we'll move on to the next question, number 5. Okay, so here Jane has a mass of 55 kilograms. She is going into a lift, which goes up to the 2nd floor. So it's saying that this lift, we presume, is on the ground floor at rest when she first starts. And she's going to go up to the 2nd floor. Okay, that's the situation. You may have to draw a free body diagram so you understand what is happening to Jane. So here's Jane. We know she has a weight force. We know she's on a lift, so there's a surface, and that surface is going to create a normal force on her. Okay? That normal force is based on the weight force. Okay? And it could be the same. It could be said the same, that the weight force is going to equal the normal force, but the normal force is equal to the weight force. Okay? That's why it's there. It says the lift accelerates up at 2 meters per second for 2.5 seconds. So it's moving up, and then it's moving at constant velocity, and then it decelerates 2 meters per second downwards for 2.5 seconds. So basically, it starts from rest, accelerates up, constant speed, and then accelerates, decelerates, or slows down, and then stops at the 2nd floor. Okay? So these two are going to be opposite velocity. This one's an upward velocity, and then this one's going to change that velocity downwards to stop the elevator and her. What is the maximum speed that the lift attains as it travels between floors? Okay, max speed would be the information we have. So u equals 0. The time for the acceleration upwards would give us the max speed. So the time would be 2.5 seconds. We want to find v, and our acceleration is given to us. It's 2 meters per second. So again, we're going to use that. We're looking at the formula data sheet, but you can know from the previous question that it should be v equals u plus at again. And because we start from rest, this will be 2 times 2.5 seconds, and we should get 5 meters per second. So now this is straight. If you really want to do the proper 3 significant figures, it'd be 5.00 meters per second. Okay, that's the 5. So that's part A. Now part B has 2 parts. Part B is asking us, what is Jane's weight when the lift is stationary? So she's not moving. Just like this free body diagram, she feels her weight force because the floor is pushing back on her with the normal force, right? The normal force is equal to the gravity force. So therefore, what is her weight? Well, That's based on the normal force, which is, equal to the normal force as well. And that's just mass times gravity. Okay, so she's 55, and gravity acceleration because of gravity is 9.8. And so that works out to 539 newtons. All right. That's part one. That's the easy part. Now, part two is the part that gets a little bit more confusing. In part two, what happens is she's accelerating upwards. So now there's an acceleration upwards. We can't have an acceleration without some kind of net force in that direction. So there is a net force this way too. Okay? It's that net force, that additional force, more than just the wave force, or more than just the normal force upwards, that's going to cause her to accelerate. Now, that normal force is equal to the gravity force when she's not moving. Well, when she's moving, it's the normal force still reacting to her wave force plus the net force required for her to be accelerating 2 meters per second squared upwards. Okay? So what ends up happening, if you look at carefully, you can see now there are two forces, the net force required for the acceleration and the normal force reacting to the wave force due to gravity on her weight, on her mass, because the floor is pushing up on her. Okay? But the floor is also the thing causing her to have this net force. So what's really happening is that the floor is still providing the normal force from her original mass, but now the floor is also additionally providing a net force to the normal force. And combined, when those two combine, what happens is that's the feeling she gets, and that's the weight she feels. So the new wave force that she feels is the combination. As you can see, the directions of the net force and the normal force are up, while the gravity force down. So they're in opposite directions. And so the net force, the normal force plus the net force is her weight that she feels. Okay? Again, remember the weight force is due to her mass and gravity pulling down on her. In this situation, the acceleration is greater than that. So we're going to write this down right now. Net force on her mass is going to be based on the acceleration that her mass feels as it accelerates at 2 meters per second. Okay? So we got mass, acceleration, and that comes into 110 newtons. So from the normal force, just based on her mass alone, that was 539 newtons from the previous part, plus the additional net force needed to accelerate her upwards in that same direction as the normal force. So we add them together, and together they equal 649 newtons up. Which is, in this case, the opposite of the wave force, so this is actually down then. Okay? Okay, we're moving on to number 6 here. What is the weight of an 85 kilogram astronaut on the surface of the Earth when the surface of the Earth's gravity is 9.8 meters per second squared? Okay, easy part for us. Wow, Fg equals mg, so it's 85 times 9.8, and well, according to my calculator, that's 833 newtons. Okay. Now, what is the wave force of the astronaut on the surface of the moon? Well, on the moon, the gravity of Earth is different than the gravity on Earth, on the moon. So the moon is less gravity because the moon is much smaller than the Earth. So its gravity, due to its mass, pulls on you less. Okay? So this time on the moon, it's the same mass of 85, but the gravity is much smaller, and so you're going to have a smaller wave force on the moon. 1/6 about. Okay? Part C, what is the weight of an astronaut on the surface of Mars? Okay, so again, it's just a matter of the same mass. Remember, the mass of the astronaut didn't change. It's just the effects of gravity on that mass is different in each of these scenarios. And so there you have it. Very easy to calculate. Weight force is just mass times the acceleration of gravity, wherever you are. All right, moving on, number 7. We can see from this pile of blocks here, and the red one is going to be struck by the hammer here, and it's going to be hit by the hammer very quickly. Okay? So how is it that the red block gets knocked out of the pile of blocks here, but the other ones above it and the one below it especially don't really move? You would think that the surfaces of the blocks would have a friction force, and they do have a friction force, okay? But because the time of the contact between the red block and the black ones is such a small amount of time, what happens is the time is so small when blocks are in contact, that means they're touching, that the frictional force does not, well, I was going to spell doesn't, let me just do it now, doesn't have enough time to accelerate the blocks above and below the red one. Probably could have typed this out, would have been much easier, but the red one. Ooh, wrong red one. Okay, there you go. So that means because there's so little force applied for such a small time, the acceleration is not enough to change the motion of the blocks above and below that red one. Okay, let's move on to number 8 here. So we have a force of 120 newtons, and it's used to push a 20-kilogram shopping trolley along the line of its handle at 20 degrees down from the horizontal. Ooh, okay, so would be a bit of advantage for us to draw a little free body diagram. So blah 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 blah. You know, you press the trolley from behind, so the force would be like this. Okay, and the angle here would be, it says down from horizontal, so that'd be 20 degrees there, that angle. And I will draw this a little bit bigger. That was kind of bad. Okay, so that angle is 20 degrees, which is the same as this angle here. This angle and this angle here are the same. That's going to help us because really we want to know what is, this is enough to cause the trolley to travel with a constant velocity to the north. Okay, so this way, velocity to the north along a horizontal path. So that means it's moving this way. Okay? So the force here that's applied is at an angle, but really we want to know the force this way. So we want to know the applied force in the horizontal direction, which we say is the x direction because it's like the x-axis. So really we want to find this, and it's causing a velocity that's constant in that direction. Okay, that's a lot of information. It says determine the horizontal and vertical components of the force applied to the trolley. Good. Okay, so I'm just going to redraw my vector diagram, and according to that, then there's going to be a downward component to it, see, and a component to the right, north, I guess that is. And that's going to create itself a right angle triangle. And I know that this angle here was 20 degrees, so that means the inside one, the alternate angle here is 20 degrees. Okay? And that's really helpful because this force was 120 newtons and it's at this angle here. Okay, so now this one, Fy, is the vertical component, and horizontal component is that Fx, Fay, and that's it. Let's find them. So we can see this one is opposite, and that the 120 newtons is the horizontal, the hypotenuse angle, the hypothesis. So I'm just going to, knowing that, then for Fy, it's going to be sine of the angle is equal to Fy, the vertical component, divided by Fa. Okay. So I'm going to rearrange this just to find this. So Fy equals Fa times sine of the angle. And so I'm going to plug that in. It's 120 sine of 20, and it's going to give me an answer of 41 newtons. Okay, 0.0. Okay, so we have that three significant 1, 2, 3. So I put in the decimal zero just to show that there are three numbers there. Okay, newtons. Now that makes sense because the angle is very small, so most of the force will be more horizontal than the vertical. Okay, so why don't we find vertical now? It's the adjacent side to this angle here, and so that's going to be cosine. I'll just do it all the long way. For those who know how to do the shortcut, you're welcome to do it. I'm just doing this for everyone. So in this case, it's going to be adjacent, which is fx, divided by the hypotenuse, which is fa. So fx, fa. And again, you can see fx is just going to be the fa value, our applied force times cosine of the angle. Okay, so we got 120 cosine of 20 and you can see it's a much bigger number, and that makes sense. We round it to 1, 2, 3 significant figures again. This time there's no decimal because it's 113 newtons, and there you go. That 120 was mostly horizontal. Okay, what is the value of the friction force acting on the trolley? Well, going back to, I'm going to just draw a quick free body diagram. If we know that the velocity is constant, then that means our F net equals 0, that the forces are opposite and equal. So if I'm going to the north and I'm applying a force this way, then that means there must be a friction force this way equal to this horizontal applied force. Okay, so that means my frictional force equals my Fx, Fax, which is 113 newtons to the south. Ooh, don't forget to write and include the direction. Why was this important this time and not in the other questions? Because in this, it told me a direction. It told me that the applied force was towards the north. And so that means this time I need to include, I could have included these ones too, but it just said the horizontal components. But it just said this time definitely include, because it is a direction for the frictional force. Okay. What is the normal force that must be supplied by the ground on which the trolley is pushed? Okay. Normally, the normal force would be for gravity on the 1 kilogram, a 20 kilogram trolley, right? But in this situation, don't forget, guys, gravity is downwards, but our Fy is also downwards. We are also using some of our applied force to push down on the trolley. So that means the ground needs to push that additional bit more than just to oppose and react against the weight force of this, just the mass of the trolley. So it also has to react to the Fy force due to the push on the trolley. Okay, so in that case, I'm just going to draw a quick one, free body diagram. So I got the normal, the weight force there, and I also have a bit of the Fy pushing down on the trolley. So that means my normal force would have to be equal to those two, but in the opposite direction. So then from that, I can come up with my equation. It's on this side. The other two are on the other side. So it makes sense. The normal force must be equal to them. So gravity for us, we haven't calculated that yet, but I'll just do it here in my equation here, and then I'll just add the Fy, which we already have as 41. Okay. So we got 196 plus 41 is 237 newtons up. You can say up, but I think in this situation, if that's north, I don't know what direction that would, it's just up. D, why is it often easier to pull a trolley than to push it? Why is it to pull a trolley than to push it? Huh. I don't know if that's true. Why is it I'm easier to pull a trolley than to push it? Honestly, in most cases, I would feel it's a little easier to push it than pull it, no? This question is not something we're going to be required to ask, but if you ever come up with this thing and you're asked to answer this, you don't really have to give, there's no definite answer to this. But if you want to say something, okay, you're welcome to say that it's because I don't know. It would have to be something like about the angle of the push that you did initially, which was at 20 degrees, I guess. And so if you pull it, maybe you can pull up instead of down. It's the only thing that would make sense in this situation. Only because of an angle of either pulling on the thing, but yeah, that's really the only thing I could think of that would make it easier, right? Is if instead of pulling pushing downwards. If you're pulling, you'd probably be pulling upwards, and then there's none of that additional force downwards that the ground has to push up against you. But honestly, you wouldn't come up with most of these questions, something like that. Okay? Number 9, we're gonna move on. Number 9 is track, of force showed. Okay, we're not gonna be looking at force graphs, so we don't do number 9 either. Luckily for you, what will be the speed at the end of the time? Well, you really want to find the speed applied force. Force times time. This is work energy. We'll get into that next year if you still live it. Now, number 10. Number 10, just do it right over here. It talks about a puck traveling on an air table. So again, the air table blows up air from the table, and the puck, represented here by the block here, floats on a cushion of air. And what happens is the cushion of air becomes the new surface for the puck to sit on. Okay? And it doesn't say anything about applied force given to the puck, and it says there is no friction. Okay, so can't be B, it can't be C. A, there's a applied force, so it can't be that. And D, there's none of the vector arrows are drawn in, so it can't be that. So it can only be B. B is the correct answer. It does have a wave force and does have a normal force because, as we said, the air becomes the new surface, and it's what's creating that normal force. And what happens is that they're equal to each other, and then the puck ends up floating on the cushion of air. Okay, moving on to number 11. We have 2 trolleys here, and they have different masses. The first one, we'll call it A, and the second we'll call it B. This is so I can refer to it. A and B together have different masses, but there's a applied force that is pushing on both of them. So when we're asked with what acceleration will the trolleys move, the trolleys will move together with the same acceleration, okay? Because the force is acting on both of them at the same time. So for us, part A, we need to combine their masses together because they become one, okay? So the acceleration is, there's only one force again, nothing about friction or anything like that. So that one force is the net force, and then it's divided by mass. And so 120 newtons, and this time the mass is the combination of these two because the 120 is applied to both of them at the same time. Okay, so we just add the masses together, and what we get? We get is 1.50 meters per second squared because 120 divided by 80 is 1.5. Now part B, what is the contact force the second trolley experiences from the first one? So the force between A and B. So there's that. And what happens is that applied force that was on A is used to move A, but also some of it is used to move B. But it's only cart A that's pushing B. Okay? The acceleration is still the same for both of them, 1.5 meters per second, but because this time cart B is lighter than 80, the total mass, what's going to happen is that cart A is actually pushing on cart B with less force than the original applied force. Okay? So it just requires less force to move that 50 kilograms instead of the 80. Okay. So if we want to know what that is, again, we rearrange our Newton's second law of motion formula, and this time it's only 50 kilograms moving at 1.5 And so that means the required F, the force between A and F, I should have labeled it A, B there like that. It's only 75 newtons. Because it only takes 75 newtons to move 50 kilograms, 1.5 meters per second. Or to accelerate it that much, I should say. Okay, let's move over to here to number 12. Number 12. A girl of mass 40 kilograms leaps horizontally off her stationary skateboard like this, assuming no friction force. Determine the following ratios. Okay, so there is her skateboard is 10 kilograms. Here is her. She's 40 kilograms. I'm just doing a little body diagram here. What are the forces acting on the ratio of the forces? Assume there are no frictional ones. The horizontal friction force on the girl, the horizontal on the skateboard. Okay. So it doesn't matter that one is smaller, the skateboard is smaller than the girl in terms of mass, because according to Newton's third law, the force of one acting on another, so this is the force of the skateboard, and this is the force of the girl. So the force of the girl acting on the skateboard and the force of the skateboard acting on the girl are the same. They're just in equal opposite directions. Okay, remember, when object A exerts a force on object B exerts an equal force, but in the opposite direction on object A. So the girl, the ratio is that because they're the same, all right, whatever their force is, 1 FG, F girl is 1, they're exactly the same, so their ratio is, we would say, 1 to 1, right? Now, acceleration is different. Acceleration, if we look at the formula, is a matter of the net force divided by the mass. However, the mass of the two, the skateboard is 10, so if we say 10 is one part, then there are 4 tens in the girl, so the mass of the two is 1 to 4. Okay? So now the acceleration of the girl and the acceleration of the skateboard, what is that ratio? Well, the acceleration, because the mass of the skateboard is 1/4 or 4 times less than the girl, what happens is the acceleration of the girl is going to be 1. It says girl to skateboard, so skateboard, girl, skateboard. All right? It's actually the inverse of this. This was the mass of the skateboard. This is the mass of the girl. This is the acceleration of the girl. This is the acceleration of the skateboard. Okay? Because mass is inverse relationship to acceleration. That makes sense. More mass, less acceleration. Less mass, more acceleration. So that's the ratio of the girl's acceleration to the skateboard. And part C, velocity of the girl, velocity of the skateboard. Well, that one, the velocity is due to the, the velocity, if they're both at rest, the velocity is just due to the time, which will be the same for both of them, and the acceleration, which is different for them. Okay, so if the acceleration is 1 to 4 for the girl to skateboard, then the velocity is, the final velocity is not based on the initial velocity. It's not based on time because they're the same for both of them. So really the only thing that changes the velocity, the final velocity, is the acceleration. So what would be the ratio? It would be the same and it would match the acceleration. See, girl to skateboard. Okay, so that's number 12. All right, we're almost there. 13. Um, a rope has a breaking tension of 10 newtons. Sorry, 100 newtons. How can a full bucket of mass 12 kg be lowered using the rope? Okay, so the problem with the bucket of mass 12 kilograms is that its weight force, which is what the tension of the rope would be on, is much bigger than the rope. I'm just going to do this first. So 12 times 9.8 to find the weight force of the bucket. It's 118 if we round it to 3 significant newtons, which is more than the tension of the rope, that the tension of the rope can hold. So let's just do a quick free body diagram so we know what's going on here. There is that, and there is that. Okay? So what's happening is this is greater than this. This can only be 100 newtons, but right now this is 118. If we just hold it, if it's not moving at all, and the rope is just holding the mass of 12 kilogram bucket, the rope would break. It would, because the weight force is too much. However, one thing that we learned from the elevator one was that if this is accelerating downwards, then that takes away from the need of gravity accelerating the bucket downwards. So if we can reduce the acceleration if we can reduce this, right, we would get a smaller weight force. So how can we reduce the acceleration? If we can't reduce the mass of the bucket, the only other thing we can reduce is the acceleration. And we do that by having an acceleration down this way already. Okay? If we are able to accelerate the bucket down, what happens is the total acceleration is still going to be 9.8, but some of that acceleration now is used to change the motion of the bucket rather than the weight force of the bucket. Okay? And we don't even need that much. We just need to make sure that the difference in the force is 0, so that the net force doesn't create so that the rope doesn't break. So if we can lower the weight force by 18 newtons or more, okay, so that's it. We can reduce this by 18 or more. So in this case, all we need to do is reduce it by 18, right? So we have a net force right now of the gravity force minus the tension. Oops, did I put N up here? That should be tension. So that means we have a difference of 18 newtons. So that means we would need to accelerate the bucket downwards equivalent to a force caused by a force that's 18 newtons. So let's find out how much that would be. So the 12 kilogram bucket, we can't change its mass. If we, sorry, let me see what the acceleration would be. The acceleration, if the net force we know needs to be that for this mass, we have 18 divided by 12. I think that'd be 1.5. So we can accelerate it downwards if we can accelerate the bucket downwards at 1.5 meters per second, then that means that the weight force of the bucket itself won't pull on the rope with as much force, because some of that acceleration's already been given to changing the velocity rather than affecting the weight force. Okay? Okay, so then you can make a statement. If we accelerate greater than 1.5 meter per second squared down, that would reduce the tension in rope to be less than 100 newtons, so that it doesn't break. And it doesn't break. There. Okay. Okay, we're going to move on to number 14 here. Number 14, a sack of wheat falls vertically from a 2.5 high shelf onto the cement floor. Which of the following, statements correctly describes the normal force that acts on the sack as it hits the floor? We have 1, 2, 3 options here. Okay, so A, the normal force is equal in size to the weight of the sack. B, the normal force is always less than the weight of the sack. C, the normal force varies in magnitude throughout the impact. D, at times the normal force is greater than the weight force. Okay, let's take a look at what's happening. Here's the floor. Here's a sack of wheat. You might incorrectly say A, thinking of Newton's third law. But remember, it's falling. As the sack hits the floor, not all the mass of the sack is touching the floor at any time. So as time goes by, more and more of the sack's mass is starting to touch the floor until, all of the sack is touching the floor. So at this point, not the total mass of the sack is touching the floor, so therefore the normal force is only so much. But as more of the mass of the sack starts to touch the floor as it keeps falling down, then you get more and more of the normal force reacting to the total mass of the sack. So it can't be A. The norm is less than the weight of this, is always less than the weight of the sack. That is not true either, because when it's finally at the floor, it's at least the same amount, right? So it can't be B. The normal force varies in magnitude throughout the impact. That is correct. You can see as more and more of the mass of the sack touches the floor, the normal force increases. At times, the normal force is greater than the weight of the sack. That is also true because of the extra velocity. Okay? Why? What is the sack doing as it goes from a motion downwards to suddenly hitting the floor and not moving anymore? Something had to accelerate it this way to stop its motion downwards. So what happens is, that means there's a net force upwards plus the normal force of the floor already due to the mass alone. Never mind the change in velocity. So the change in velocity created a net force, and the mass of the sack itself causes a normal force. So that is true. If you add these together, That's more than the normal force alone. Okay? Very similar to the elevator question. All right. What is this? A carbon number 15. A car begins to roll down a steep road, a rate of 5, 1 in 5. So 1 in 5 would be like this. So that means you every 5 meters you went, you dropped 1 meter. Okay. If friction is ignored, determine the speed of the car in kilometers per hour. After it has traveled a distance of 100 km, it begins its journey at rest. Okay. See what we got here. So we're gonna right now we have everything in meters, and our acceleration due to gravity is meters per second. So what does this tell us? This tells us the angle. Okay. So what we have is the opposite side and the adjacent side. So we got to find the angle first, because if I draw a free body diagram, the only thing acting on the car is the wave force and the normal force. Okay, so that means we need to know this angle to find out there is a net force this way, because that's the way it's moving. It rolls down a steep hill, so that means it started from rest, okay? And then it went a distance of 100 meters. So we have this is 100 meters down the slope, though. Okay, be careful with that. Initial velocity was 0. What was determine the speed? Okay, we want to know what the final speed is. We're missing something here. We don't have a time, so it must be acceleration that we must define first, okay? And the only way we can find acceleration is if we know the net force. Determine the speed of the car after. Okay. Okay, so let's take a look at this. What do we have here? We got that. I'm just gonna draw myself a vector diagram here. Oh yeah, I gotta get the angle first, don't I? Okay, no problem. Is tangent of the angle equals the opposite side over the adjacent, so 1/5. The angle equals 1/5 is 0.2. So inverse tangent of 1.2, the angle is 11.3 degrees. Again, 1, 2, 3 significant figures. Okay, so here it is. I'm going to draw my vector diagram here. This is 11.3, the F net. Says it traveled. F net. Does it say how much? Is there more to the question? Nope. That's it, huh? Okay. I just travel distance of time. So we need to find the acceleration. If we find this, I can get the F net. So F net would be these two we know is a right angle triangle. So we got sine, because this is the hypotenuse and the opposite side. So sine of the angle equals the net force divided by the weight force. So the net force equals What's the mass? We don't have the mass, right? So it'd be mass times gravity times sine of, well, let me just move this over. I'm running out of space here. So F net would equals mass times 9.8 times sine of 11.3. So let me just find that first. Okay, so the F net is equal to 1.92, these two numbers, times mass. Okay, because it doesn't say what the mass of the car is. Okay, so we have that. Now, if the acceleration of the car is going to be the mass of the car, right? We don't know what it is. Doesn't matter, because our F net is divided by the mass, right? And our F net is 1.92 mass, and now we can see it's divided by the mass. Okay, so even though we don't know the math, it's okay, because both these numbers that we're working with is the mass, and so they would just cancel out like that. So that our acceleration is going to be 1.92 meters per second. Okay? And so now we're asked to find what is the final velocity after 100 meters going down the hill there. And so that acceleration is that direction as well. So let's put that in the equation. Based on these 1, 2, 3, 4 variables, I know that one now. I'm going to put this in there. And based on that, I have this equation to work with. And so it says it starts from mass. We already know that's 0. So that's 0 plus 2 times 1.92 times 100 meters. Okay? And so that 1.92 times 200 is going to be 384 meters per second, but we still have the square root of this, right? So that would be, the square root of that one is 19.6 meters per second. Okay, but it asked us right here, what is determine the speed of the car in kilometers per hour? So we need to convert meters per second to kilometers per hour. It means that we need to multiply by 3.6. So the final velocity is 19.6 times 3.6. 70.6 kilometers per hour. Okay? Wow. So just work through what you have to at first, and if you find, like in this question, oh, I don't know the mass, but acceleration, regardless of that, is dependent on really the net force acting on the mass. Correct. But remember, in this equation, net force, the weight was part of the weight force. So the mass was part of the weight force. And then because acceleration is divided by mass, that unknown m just cancels out. They just cancel out in most situations. And we don't notice that in most questions, but that's what happens. Mass cancels out. Okay. We have 3 more questions. It's a long one. A boys' racing set includes an inclined track with a car which accelerates at half of gravity. At what angle is the track to the horizontal? Okay, so we'll draw a quick free body diagram, and it says this A is 4.9 meters per second. And we got to find out what angle creates that acceleration, right? Do we know the mass of the car? No, again, so again, we don't know the mass of the car. Does it really matter for us? As you saw in the previous question, not really. Okay. Okay, so if this is due to the net force, remember, if we draw a free body diagram, Fg is mass times gravity, right? That's the equation for it. And then our net force and gravity, and this one, we want to find the net force. Whoops. It's mass times acceleration, right? And you know, A and G are both accelerations. So if I only want, really, the mass doesn't change for these ones. See? So at what angle here do I need, so it creates half G becomes 9.8. So that 9.8 becomes half of that, which is 4.9. Okay, so just the acceleration is 4.9 from the original 9.8. So what angle will give that for us? Okay, so instead of writing the net force and the wave force, we're just going to write the accelerations for the values of these sides, because their net force was just times mass and the wave force was just times mass, and we don't know mass, but they can cancel out. So sine of the angle equals F net, which we now have changed only to just the accelerations. So this side's acceleration divided by this side's acceleration. Okay, and so there it is. You can find that it'll be sine inverse of 1/2. This is 1/2, 1, 2. So that would be 30 degrees. Okay. Okay, so number 17. We've done one similar to this. Again, drawing your free body diagram of what's going on. We have the angle, which is 35 degrees. We have wave force. We have normal force. We do have a friction force that we're going to include later, because right now we want to find out what is just the net force along the slope due to the normal force and the gravity force, right? And to do that, when there's an included angle, is we draw a free body diagram. Okay, so there is a 250 Newton friction force, and it says that the mass is 70 kilograms. And what was its acceleration? And that's due to a net force here. So when there's more than one force, we have to draw a free body diagram of those forces. Downwards for the gravity, at an angle here for the normal force, and then the net force between those two is down the hill like that, and the angle goes opposite that net force always, okay? And so we know these two, the net force and the normal force, are perpendicular to each other, because one is perpendicular to the slope and the other one follows the slope. All right, so again, I have a hypotenuse in the opposite side, so it's sine 35 equals net force, the opposite divided by the hypotenuse Fg. So net force is just Fg times sine of 35. Okay, and that's going to be 70 times 9.8 for the G, FG, and then sine 35. Okay, it's 393 newtons. Now that's just the force created by these two, the net force of those two. But now we have to consider the friction force that's going to resist that. So that means our real net force is really the second one we'll say is the original net force minus the friction. Oops, minus. So 393 minus the 250, okay, and we get 143 newtons. So then, what is his acceleration? His acceleration is going to be the net force, the second one divided by the mass. So 143 divided by 70 equals 2.04 meters per second squared. Okay. And I'm at my last page here. Okay. Hold on. Okay, last one, number 18. Sketch, draw vectors to indicate the force that act on a tennis ball as the tennis is being struck. Okay. Tennis ball. Boom. And a little bit of gravity, of course. So there's the FA, there's the FG. I mean, there's a racket here, of course. Sorry about the prettiness, but that's it. That's the racket. Okay, there it is as it's getting struck. What is it? And so this is the direction of travel. And then the second part, B, what happens when it's after it's struck, it's in the air now. Gravity, of course, still acting on it. It's still traveling this way. However, now there is air resistance, okay, in the opposite way that it's traveling. And it should be less than the gravity because it's not slowing that too big. It's not as strong as the applied force. But it is going to slow it down. Okay, so you can see air is resistance is opposite direction of the travel, the motion. Okay, that's the end of this review for chapter 6, guys. Good luck. If you have any questions, you should send me an email. I'm going to post this for you guys right now. See you next week. Good luck on your exam.